Hi everyone, I'm really excited to interview Professor Chris Williams. He's an artistic professor at Department of Architecture and Civil Engineering at Chalmers University. He joined Ted Happold's group at Arup in 1972, where he worked with on Frei Otto's Multihalle gridshells in Mannheim and was responsible for the structural analysis and physical model testing. In 1976, he came with Bureau Happold to the Department of Architecture and Civil Engineering at University of Bath. His research interests hinge on the relationship between geometry and structural action as applied to towers, bridges, fabric, and shell structures, as well as the response to those flexible structures to wind. So without much ado, we'll start in the interview. So Dr. Williams, can you share us what inspired you to become a structural engineer?
Okay, I think for most of us, these things happen a bit by chance and so on. So I always enjoyed maths and science, particularly physics. I also enjoyed taking my bike to bits and that sort of thing, making model aeroplanes. And so I thought I would do engineering. And at Cambridge, you don't specify what sort of engineering you're doing, you just do engineering and then you specialize later on. Again, as I like maths and I found structures interesting, I specialized in structures.
What's your structural design philosophy?
Right. I think the most important thing is that when you design a structure, you have a clear idea of how you want it to work. These days, because you can analyze everything quite easily on a computer, it's very tempting to not really think about things too much. But I think it's a good idea to have something which is a very simple mode of structural action. And then when you analyze it with the computer, you hopefully find that it behaves as you thought it would. I think also if it's relatively simple, then that hopefully will mean that it is reasonably elegant, relatively easy to build.
Can you share how your philosophy changed over the years?
I don't suppose it has changed that much. I suppose the important thing to realize is that almost always you are working with a group of people, and different people come up with ideas, and a design will always evolve. And so you have to be prepared to participate in that and try and move the design in the direction that you think is most appropriate. I think when you finished a design, and you look back at it, you always say that there are things that you would have done differently. And if you don't think that, then it means that you aren't really learning from the process. I think that obviously, and the thing about civil engineering and structural engineering is that if you make a mistake, then that can have very serious consequences. And it may just cost lots of money, or if you're really unlucky, you may have lots of people being killed. And engineers tend not to talk about that too much, especially in front of architects. But certainly, I think that part of the advantage of having a relatively simple structure, or a structure which you can understand in a relatively simple way, is that being able to demonstrate that it is hopefully safe is easier than if you've got something which is a complete mess. But going back to the issue about teamwork, the interesting things there, of course, is from an engineering point of view, is that sometimes you are presented with a structure which doesn't make very much sense. And one approach to that is just to try and make it work as a sort of demonstration of your virility, if you like. The other is to try and persuade and get things changed. And the interesting thing there is how honest you should be in that discussion, whether you should actually be rude about something that somebody has produced. Different engineers work in different ways. So Ian Liddell, who you may have heard of, he was always very clear in expressing his views, which was good. And he had a very direct way of putting that, which was always nice to hear.
How does a day in your life look like?
I'm now retired from teaching, undergraduate teaching, whereas so in the past that would have been quite a large part of my life. So I probably spend, in terms of work, most of my time working with the PhD students at Chalmers. If a project comes along, then that tends to be very time consuming. And what you have to do is to essentially drop everything and work on the project. But at the moment, I haven't got any active projects. So it's, in terms of work, most of my time is spent doing research, which basically means doing maths as much as possible.
Mm-hmm. If you can name a book which had a biggest impact in your life, what would that be and why?
I enjoy reading all sorts of things. So I just finished reading War and Peace by Tolstoy, which is a very interesting, enjoyable book, but probably doesn't have that much impact on the way that one would work. In terms of work, I guess it must be Green and Zerner, Theoretical Elasticity, because that's one of the very few books which combines geometry and structures all in one place with a consistent notation. It's particularly relevant to things like shell structures, maybe less so to other sorts of structures. The problem with maths is that you don't really know what you need to know. And it takes quite a long time to learn. And so you may end up learning lots of stuff which is not very useful. Also, of course, you tend to be constrained by what your teachers know. And your teachers, in turn, are constrained by what their teachers knew. And of course, because computation is used so much now, that very much changes what you need to know. So anyway, in answer to your question, I would say Green and Zerner. When I'm not using Green and Zerner, then it's almost certainly some book by Timoshenko and Wyonsky Krieger, I can't say his name, Plates and Shells anyway. So so those books are probably the ones that I found most useful in terms of work.
Can you share us the challenges faced in your career and how did you resolve it?
I've been quite lucky in the sense that I grew up at a time when there was a lot more optimism than there is now. And obviously we've got COVID and stuff like that. But even before COVID, there's a feeling that the past was probably better than the future. Whereas when I grew up, the future was seen to be better than the past. And part of that optimism you could see through the work of people like Frei Otto, who had a very sort of optimistic view of the future. I guess I was also lucky in the sense that when I started work, we didn't really have computers at all. And if you wanted to communicate with somebody, you used the telephone or you'd send stuff through the post. And if you wanted to do some calculations, you'd use a slide rule. a slide rule is? You know what log tables are?
Yeah.
Okay. A slide rule was a sort of thing, and looked a bit like a ruler, but it had a bit in the middle that you slid along. That's why it's called a slide rule. And it was basically used for adding the logarithm of numbers together to do multiplication. So you did multiplication and division with this physical thing. And so that was quite nice. It was relatively slow. It would take you a whole day to design a portal frame, whereas now you do it in 5 minutes on some software. So it was nice to see that change taking place. Also, it was quite nice that, to begin with, there was very little software available. So you ended up having to write your own software. And that was quite good as well. So that was nice. So it meant that on projects, say the Great Court, that because there wasn't software available, we wrote our own software, which is much more satisfactory than using off-the-shelf software. When I say it's satisfactory, more enjoyable. You feel as though you're more involved. I think now we're sort of reaching the stage where a number of things are sort of coming together and making things more difficult. Maybe that's just, I think it is, certain things are more difficult. So when I started doing research, if you were interested in a certain topic, you'd try and assemble all the papers you could find on that topic. And that was quite time consuming because you had to go to the library, you had to look through all these papers and stuff. Then you probably had to order them, and they'd come in a month's time or something. But after that, you'd assemble all this stuff and you'd have maybe 10 papers or whatever. Now you do the same thing. It's very much quicker. You do it in a day or two, but you end up with sort of 500 papers. And so you then start struggling through all this stuff. And there's a real sense of overload, which I guess will become worse. So in 50 years' time, you'll just be completely buried in some sort of sea of stuff. You'll have AI or more AI to help you. So, and also I think we'll see that a lot more in all sorts of areas of design and everyday life. So, for example, in architecture, so you're studying architecture, yeah. So I guess at the moment, you probably spend your time working out things like how a building is going to be used, working out circulation and stuff like that. As you probably know, there's software that does circulation. So at some point, people will stop really thinking about circulation and they'll just say, oh, we have to simulate this. So they put their building into some software and it tells them how the people are going to use it. And then one of the interesting things is whether people will develop aesthetic engines so that you draw your building and ask the computer whether it's pretty or not. And the computer will say, it's fairly pretty, but you need to do this or do that. I suppose aesthetics is quite subjective, whereas structures is not quite so subjective. And I suppose the more subjective something is, the more there's scope for human input. But I guess that will probably change. You know, more and more areas will, I guess, be taken over by AI, or people won't feel confident to make decisions unless some computer says that's okay.
I see. And I totally feel your first point where sometimes even I'm doing research, there's so much stuff out there on the internet that it's difficult to find quality stuff in all this noise.
Yeah.
And the second point of working with AI, what do you recommend a student or a professional who think that there's a lot of tasks which technology can do better, than the current work procedure. And there are times when they might get scared. Okay, what should we focus on? So, what will be your perspective on like how should one balance the knowledge and the technique?
One thing I can say, and that was that quite that Ted Happold always used to say that one of the most important things was that the design process should be enjoyable. And there are obviously certain tasks which computers can do which are very helpful, particularly if used in the right way. So something like email, for example. So the first project I worked on, we were able to email drawings, was the British Museum. So that was very nice. It meant that Philomena and Russo at Foster's and I could work together, sending drawings backwards and forwards. Whereas in the past, you either had to go, you had to be in the same office basically, or you had to rely on the post, which was obviously quite slow. So that was good. On the other hand, as everybody knows now, in any sort of business, you get this sort of email overload where everybody thinks that they can send all sorts of crap to all sorts of people and you get all this stuff. So I suppose the thing is to try and preserve the aspects of the work that you enjoy. For an engineer, for example, or an architect, you enjoy drawing with a pencil, sketching ideas and things. And it's obviously nice to be able to say, scan those and send them to your friends or do it on an iPad or something. And so that's obviously great. But then what you want to try and do is to not lose those aspects that you enjoy. And yes, I suppose there's all sorts of issues in that, and that in the sense that there's also what happens with your, or how you see your career progressing. One of the problems is that if you're successful, then you end up basically not being an engineer or an architect anymore. You end up being a manager. So I think it's important that to try and strike a balance there. But that's where teamwork comes into it. And again, with Ted, one of the good things about Ted was that he was very good at delegating and also very good at choosing the right people to work with him so that he could delegate. I think at the moment there's a bit of an issue with a generation gap in the sense that young engineers, your sort of age, they're all sort of good at things like Grasshopper and stuff like that, and Revit and what have you. Whereas older engineers don't really understand what on earth we're talking about. But I guess that problem will continue because you probably know about Revit and Grasshopper, but in 20 years' time, probably those will become out of date. And there'll be a new generation of young architects and engineers who have this new stuff, and you won't understand what in the hell they're talking about. So
I just wanted to know how does one balance the theoretical knowledge apart from keeping up with the technological advancement.
Okay, that's a question it's almost impossible to answer, really. If you let's take another profession like medicine, something like that. Now, in the past, to be a doctor, you didn't necessarily need to be particularly bright, but you've always needed to have a very good memory. So I think you had to learn all the names of all the bits of the body, all the bones and stuff. And then you had to remember all these different diseases and the symptoms that each of these diseases have and so on. a tremendous amount of stuff you had to remember. But I guess now that sort of knowledge is not particularly relevant, because you can obviously, if you want to know which bone connects your thigh to your foot or whatever, you can just look it up on Google. And I think so, there's a whole range of different professions which are only now fully appreciating the influence of technology. I used to, I think, perhaps think a bit like that, but it implies that architects have a particular aesthetic sense which other people don't have. And I assumed that there was something in their training which gave them that. But then after a bit, you realize that actually that's not true, that everybody has some sort of aesthetic. And if you're, say, an engineer designing a bridge or something like that, to say that an architect, you need an architect to look after the aesthetic side is ridiculous. I guess there's always been this sort of tension, if you like. And so in car design, for example, there would be engineers and stylists, and there was a sort of separation. But ideally, I think one would, as far as possible, do away with that sort of distinction and think of ideally you have people who are interested in all aspects. Obviously, there are certain things that architects do, work out how big toilets have to be and how many toilets you need and stuff, which engineers are not usually so interested in. But I think when you're working on a project, even though some people call themselves architects and some people call themselves engineers, then essentially they are all working together. And there are certain areas which seem to move backwards and forwards from engineering to architecture. Architectural geometry, for example, if there was something complicated with the geometry of a building, then they used to get the engineers to do that because they were good at maths. But then once computers came in, architects realized that perhaps they needed to get quite up to speed on all this maths and computing. Because obviously it's very important for the aesthetics of their building. So something like architectural geometry is somewhere in the middle. It's not really, is it architecture, is it engineering? But again, this is not a new thing, because if you go back to, say, do you know what stereotomy is? Yeah? Stereotomy? Do you know what stereotomy is?
Stereotomy? I don't.
Okay. Stereotomy is the science of cutting stones for buildings made of masonry, cathedrals, houses, and so on. There are textbooks on it going back 500 years, written by people like Philibert Delorme, for example, who was quite a well-known French architect. And in the past, both engineers and architects would have been taught stereotomy. It's basically quite three-dimensional geometry, and you would learn methods of drawing and so on in order to cut the stones to these complex shapes. Essentially, it was equivalent to modern architectural geometry, if you like. So in the past, you would have had a whole range of people who would perhaps, they would have gone by different names. There'd be some people who are good at stereotomy, there'd be masons, there'd be people who call themselves perhaps an architect, and so on, all with their different roles. And I think that will always be the case. But of course, again, going back to the increased use of computers, who you need and what they need to do is will always be changing. So in the UK, we have people called quantity surveyors. So their job used to be to take the design and count up how many bricks you needed, how much concrete, how many reinforcing bars, etc. Now, one would assume that role has essentially disappeared because Revit or whatever will tell you exactly how many bricks and so on you've got in your design. I think they still have them to look after the contract side of things. Yes, so exactly how you assign all the different tasks involved in building a building or making a bridge or whatever is to a certain extent arbitrary. And obviously there's been a long history of separation of design and making, so that if you're an architect and you design a building, you don't then go out with a shovel and start making it. In other areas, that separation is not so clear. So if you're an artist, for example, you may well make the art yourself.
I think this is a point which I would like to hand over to Anand to talk about your professional work and projects.
Yeah, hello.
Hello.
Yeah, you have been extensively involved into research as well as practice in that career. With when we talk about practice, then you have been involved in projects in Mannheim, Gardens by the Bay, glass houses, 7 building roof, and the list goes on. You have also been involved into research mainly at Bath and now at Chalmers. So I wanted to ask you that what are some of the key aspects that you could share in terms of critical things to take care of while designing mainly grid shell kind of structures, and how did you bring practice and research together, because that is where most of the people struggle to bring research into practice and practice into research to relate the two things.
I suppose the big difference between research and practice is that as far as research is concerned, you have quite a lot of freedom to decide what it is you want to research on. Although, of course, you're constrained by having to try and get research grants and all that sort of thing. When it comes to real projects, then I suppose the big issue is that you can't just say, oh, I think I'll build a bridge here, or I think I'll build a building or whatever. Yeah. You have to rely on chance to a large extent. And if you're lucky, you will be in the right place at the right time. And of course, you can do things like enter competitions, which are good fun. Of course, you normally don't win, but even so, it's good fun. And to get involved with the sort of relatively small projects that, say, Akim has done. Mm-hmm. Yeah. And I don't know if the work that Emil Adils has been doing in Chalmers. Yeah. So that those relatively small experimental projects are good fun as well. I suppose the difficult thing is that every time a new grid shell is built, it in some ways reduces your choice, because you don't want to just repeat what somebody else has done. Yeah. On the other hand, there's no particular reason why you can't be inspired by other people's work. The difficulty is to not just copy it. Yeah. But I suppose if you look back to masonry, there would be thousands of masonry domes and vaults and so on have been built. And over time, these designs evolve and become more sophisticated. Yeah, I guess grid shells will be with us. Well, we've had grid shells for, how long do you reckon? 200 years or something. There have been many steel and glass houses. Yeah. And there's been things like the Grand Palais in Paris and so on. Mm. So the idea of covering a public space in such a way that you have a lot of natural daylight is something that people naturally want to do, at least in the temperate regions and cold regions.
Okay.
Yeah. Yeah, so I guess grid shells probably are here to stay.
Yeah. And you have been involved in Multihalle, Mannheim, as well as the Seville Garden Roof. So the Seville Garden Roof is very recent as compared to Multihalle, Mannheim. So what were the challenges faced in Multihalle, Mannheim, and how they were, you tried to overcome those challenges in Seville Garden Roof, because both are elastic timber grid shells and they share a lot of similarities in many aspects, I guess.
Yes. Well, I suppose the strange thing is that the biggest one and the most challenging one was the one that we did first.
Yeah.
Of the timber grid shells, the more recent ones have been less challenging. What happened on the Multihalle is that there were originally other engineers for the project. And I don't know exactly what happened, but they felt that they couldn't really cope with the project. And so Frei, who met Ted Happold in Saudi Arabia, I think, suggested to Ted that we might like to be the engineers at Arup in London. And Ted said, yes, okay, which is very brave of him. And so he turned up in the office one day and said that we've got this project in Mannheim. And so we had various information. We had, I think at that stage, Frei was already building his hanging model. And Linkwitz was doing the computer model. But we didn't have all that information. So to begin with, we built a model of the S01 grid shell, which Frei had done earlier. And from those model tests, we were able to show that the original design for Mannheim just wouldn't work. The original design just had one layer. In other words, members going in, just two sets of members like that. And so we immediately said that we had to go for a double layer, in other words, two sets of members in each direction. And we also added cable bracing. And all of that came from the S01 model, which is a fiberglass model about 1 meter across. For some reason, engineers and architects seem to struggle scaling model test results. And I'm not quite sure why. Physical models are still quite useful because they give you a very tactile feedback as to how a structure is working. So we used those scale model tests, and they showed that we could just about get it to work. It was interesting talking to the people at Arup then, because there were the original generation of people. So we had a meeting. So Ted and I had a meeting with Arup himself and Ronald Jenkins to discuss the project with them. We also talked with John Blanchard and all the sort of technical people at Arup to discuss it with them. People who worked on Sydney Opera House, for example. So that was quite interesting. And as with all projects, there's lots and lots of detailed day-to-day stuff that you have to do. Like we had there was no CAD in those days. So we had to find ways of doing drawings of curved arches and things like that. We had a little desktop computer which you had to write programs in, and then it was sort of had this. It would then print out sort of strips of data, which you then work out and put onto your drawing.
Yeah.
So all that was quite fun. So I guess the big change in terms of computers was between then, in the mid-70s, well, early 70s that was, and then British Museum, which was the late 90s, by which time we had desktop computers and stuff. So the geometry of the British Museum was done on a Macintosh Performer, which was a home computer from the mid-90s. Yes, but it was very exciting, and I was very young then, and so it was good fun going with Ted or Ian out to Stuttgart to see Frei and the other people at the IL. I guess you've been to the IL.
Yeah.
Yeah. So in those days, it was out in the countryside. It wasn't surrounded by all those other buildings.
Yeah.
Yeah, so that was all good fun.
Yeah. And in the document, you mentioned that was something related to grid buckling in timber, which was one of the major challenges you faced during construction. Yeah.
Yes. If you're doing a slender structure which works in compression, then buckling is always an issue. And in some ways, the more perfect the structure, the more it's an issue, because then the more perfect it is, the more imperfections influence its behavior. With timber, though, the big problem is that you don't really know what the stiffness is. That if you apply a load to it long term, you get a lot more displacement than you do in the short term. To a certain extent, the same thing applies to concrete as well. And creep buckling is where the structure moves over time, becomes more and more imperfect. And as it moves, you get more and more bending moment. And so it creeps more and more quickly. And so it's pretty bad news, but you have very little information as to the creep behavior of timber, which is understandable because you can't do tests that last 20 or 30 or 40 or 100 years.
Yeah, yeah.
Dragos Niatsu and I, he was a PhD student a few years back, we did a study on timber versus steel for grid shells, taking into account things like sustainability and all that sort of thing. And we decided that the best thing to do with the timber was to cut it down and burn it and use that to generate energy to produce steel and build a steel grid shell. That was a bit of a joke, really, because people always say that timber is very sustainable and you should build everything from timber. But it's I think when it comes to using choice of structural material, you want to use what is most appropriate for the particular circumstance that you have, taking into account all sorts of factors, including how long the building is going to last, and so on, and taking into account energy in use as opposed to energy used in construction and that sort of thing. But material choice is always an interesting topic, and it is partly an engineering decision and it's partly an aesthetic decision. And obviously taking into account things like sustainability and so on.
Yeah. And I think you covered most of the questions, like the questions which we had further as well. Most of the things I see you directly or indirectly covered them. And it's also like around 1 hour now.
Okay.
So maybe I would like to ask you one more question, is that how do you see the future of lightweight structures? Because we have so many disciplines and everything is integrated right now with machine learning and this research done at various institutes on geometry and the whole computer and these things coming together, where some institutes are also studying history and bringing that back in, like work done at Block Research Group, or maybe extremely lightweight materials being researched for the Mars project. So what do you think about all this in context of future when it comes to lightweight or efficient structures?
I suppose the most important thing is that we build things for people to use and hopefully to improve the quality of their lives. And I suppose what has changed is that nothing seems to be as simple as it was in the past. Because we're much more focused, for example, now on energy, and building lightweight of itself isn't necessarily the most energy efficient or the most sustainable solution. So, for example, Mannheim, Mannheim was built was a temporary, intended to be a temporary project anyway. Yeah. But as you probably know, the idea is you have to put the heating on to melt the snow on the roof. And that's not a very sustainable approach. And of course, there are discussions going on at the moment trying to solve that problem. Yes, I don't think lightweight structures are going to solve all the world's problems, in particular inequality of opportunity, political problems with dictatorships and so on. But I think people naturally want to build things and create things. It's a sort of inbuilt human desire to do that. So people will continue to want to build things, and so much depends upon how we organize our lives. At the moment, we've got this big change where everybody is now working at home. And things like town centres will perhaps have different uses. Yeah, but I guess it will always be something that there'll be some people who are interested in it. But there'll be times when I think every sphere of activity seems to go through golden periods, and then there's a bit of a lull, and then it comes back again. For example, 20 years ago, nobody had heard of Frei. So he was very well known 40, 50 years ago. Then he was forgotten about, and now everybody is talking about him again, which is quite nice for me because people are therefore interested in the fact that I knew him. Yeah, but so I think there's always things that will happen in the future, but you can't predict what they will be. Yeah, I think that's all I can say on that.
Yeah. Thank you. Yeah, I think now I would like to give the mic back to Mayur.
Okay.
Let's see his questions.
Yeah.
Thanks a lot.
Yeah, I had 2 to 3 questions which I wanted to ask you regarding advice to students section. So if you have some time, I can.
Okay.
Is it?
What I would say is that the most important thing is that if you're interested in something, then be prepared to teach yourself. Because there are so many possible things that you might be interested in knowing about. And the chances are that there won't be anybody at your university or whatever it is who is perhaps interested in that subject. And that doesn't matter because, especially now, because so many books and so on are available, is that you just sit down and teach yourself. Of course, the problem, as I think I've already said, is that you don't really know what will be useful. But I guess the thing to do is to start with the things that you think are interesting and inspiring, and then work from there. So that's what I would say.
Yeah. And what is the best piece of advice you have ever received till date?
I suppose the best piece of advice would be is to assume that everybody else is a complete idiot. What I mean by that is, I don't mean that you literally think that everybody's an idiot, but you should, it's a good working hypothesis if you're an engineer, because if you say, go to speak to somebody about some problem that you're worried about, then if that person says to you, oh, it's all right, that won't be a problem, then you shouldn't just accept that. You have to say to them, oh, why is it okay? And because you then have to understand exactly whether or not something is a problem. And this might be a problem, say, I suppose you're worried that you're making a steel structure and you're talking about the paint, what paint you're going to use. And the person you're speaking to says, if you use this paint, then it's okay. But what you have to say is, how do you know it's okay? And then always dig deeper and deeper. Partly because it's interesting, and partly because things can go wrong if there's, say, a misunderstanding. And I guess one of the things about engineering is that there are so many different aspects to what we do. Metallurgy, there's welding, there's painting, there's soil mechanics, there's fluid dynamics, and so on. And obviously you can't understand everything there is to know about all of those things. But ideally you should always be questioning. And of course, through questioning, sometimes it means that you can solve a problem by actually just avoiding the problem altogether, rather than throwing technology and money at it.
I see. And can you explain Cohn-Vossen's rigidity theorem?
Theorem. Right. Okay. Yes. Just a moment. Okay. So can you see this? This is half of a football. And I put the it's a bit different. I put the two halves together like that. I can try anyway. Put the two halves together to make a complete sphere. Alternatively, I could take this iPad and I could put this on here. Okay, now when I put that on there, it's actually, now it's quite stiff. Whereas when I've got it like this, it's really very, very flexible. Now, I suppose the first person who looked into this was Raleigh. He wrote a paper on bells, Lord Raleigh, because if this was a bell, you hit the bell and it would oscillate. And when it oscillates, it bends, but it doesn't really want to stretch. Now, if you've only got half of a sphere like this, it is very flexible and you can roll it up. And what happens when you do that is that the Gaussian curvature remains constant, which is the product of the two principal curvatures. And you can see it gets much more curved this way and it becomes less curved that way. If you have a complete sphere, then what the Cohn-Vossen theorem shows is that you can't deform it at all without changing lengths on the surface. The problem is, though, that if it's a very thin sphere, then it can buckle, which basically means that you get a small amount of extensional deformation and a large amount of bending. That sort of explains the Cohn-Vossen theorem.
Yeah, actually, that was quite insightful when you showed us or demonstrated through that example.
Okay, so the here we have a grid shell, and this is made of a woven wire mesh, and this is actually quite flexible. And the reason it's flexible is because it's only got wires in two directions. And when I load it, the squares on the surface become diamond shapes. And this is very similar to the S01 model that we built. In fact, you could take this and you could put some loads on it, maybe like this coffee cup and so on. And from that, you could predict how a structure like Mannheim would behave by scaling the results. Do you want me to tell you how to scale the results, or do you know how to do that?
I don't know.
Okay, it's very easy. Let's imagine that you built a large structure which was a perfect scale, a perfect scaling up of this. So it was made from steel, and all dimensions were increased by, say, a factor of 100 or something. So the span was increased by 100, the diameter of the wires was increased by a factor of 100, and so on. Then if you did that, then dimensional analysis, that's like Reynolds number and all that stuff, would tell you that the full-scale structure would carry exactly the same load per square meter as the model in kilonewtons per square meter or whatever. So that means that there's no scaling required at all, and provided that the loading per square meter is kept the same. But then you say, actually, this is made of steel, whereas my model, my real structure is going to be made of timber, say. You then say, I'm probably mainly interested in the Young's modulus, the stiffness. And so you then scale your result according to the Young's modulus of timber versus the Young's modulus of steel. You might then say, actually, my member sizes are a bit different. I haven't scaled those. So you then say, it's probably the EI value that I'm interested in, and that the collapse load is proportional to the I value. So if you make the members twice as big, the I value goes up by a factor of power 4, which is 16. So you then say that you factor the load by 16. If the spacing was different, you then say, well, double the spacing, I probably half the load, in the sense that I'd be reducing the bending stiffness by a factor of 2. So that's basically how we scaled the results on Mannheim. Now, what's really interesting about this is you can see that because this has got this extra flexibility, it does actually, the load is still going up even after these really big displacements. Whereas this is much stiffer than this, because it's fully triangulated. I'm going to be a bit careful now. When I load this, the load is very stiff, and then the load suddenly drops, and the load is really dropping. So this is very imperfection sensitive, but very efficient, whereas this is less efficient and less imperfection sensitive. Okay, so that's the Cohn-Vossen theorem for you.
Yeah, and I remember I watched your video on YouTube about your lecture, and you said the more efficient structure is, it's more sensitive, so you have a
Yeah,
like a balance. Yeah.
that's right.
Cool. Can you share why? I know you might have explained briefly about this. Why is bending stiffness more important to stop shell buckling?
Well, they're both important, both bending stiffness and membrane stiffness. But the buckling load is roughly proportional to the square root of the product of the two. Increasing the membrane stiffness is the most efficient way of doing it, but it also leads to this imperfection sensitivity. And of course, the other thing is that it's not just the shell itself, it's the shape of the shell, which normally aren't just spheres, but it's also the boundary support. Very often roofs like the British Museum roof are on sliding bearings, so it can't thrust outwards, it just expands. And that makes it a lot less efficient. We did some of the grid shells by Schleich. Some of those have got tension ties inside. And we tried to persuade Foster's to allow us to put tension ties in the great court, which would have made it more efficient. But it probably looks better without them. But these decisions are very difficult to make, and you have to make them very often quite quickly. And since that time, lots of people have done various studies on the Great Court, investigating different grid patterns, for example.
I've observed is there might be some countries in the world who might not have the latest technology or available resources to make this kind of structures. So what will be your piece of advice for people who wants to create such amazing structures but have some constraint or limitations?
I don't think it's necessarily an issue in terms of constraints, because people have always built the most amazing structures, even with the most minimal resources. And actually that can be quite a positive input into the design process, having constraints. And that's in some ways how ingenuity comes into it, where you don't have all these things like robots and so on. So I don't see that as a drawback. In some ways, the biggest problem with lightweight structures in general is that the structure is only there to support the cladding system, whatever that is. Obviously, now we have the possibility of cladding things with glass, but essentially the structure is only there to support the cladding. And that is in some ways, the biggest constraint.
Got it. And my last question for the interview is, how can one develop the artistic or intuitive understanding of this kind of structures?
I think you certainly need to be aware of all sorts of things around you. So Frei was always referring to Darcy Thompson on growth and form. So that means that you're inspired by the natural world of plants and animals. It's important to, as I said, think about everyday objects. We've already talked about this sieve. And if you're interested in fabric structures, then there's fabric everywhere, all around you. And in order to understand how fabric behaves, you don't really need sophisticated software. You just need bits of fabric. And you probably, I don't know, here's my glasses case, for example. So this is a shell structure. So something like this, all these everyday objects tell you as much about these structures as fancy textbooks and lectures from professors and stuff.
I see. So being more observant in our day-to-day environment and noticing.
Yes, exactly.
Okay. And how can our listeners follow you and your work?
Oh, I do have a website, which is do you want to know what the web address is? Structure-geometry.eu. So, well, we haven't talked about Brexit, but obviously the fact I've chosen the European Union web address gives you my views on that.
Okay. I think this was an amazing interview. I wish I could go on because I was learning each and every time when you discussed and answered a question.
It's been a pleasure. Okay, right. Bye-bye.
Yeah, thanks a lot. Yeah, bye-bye. See ya.
Bye.
Thank
Bye.
you. Bye.
Have a nice day.